In aeronautics, transonic refers to the condition of flight in which a range of velocities of airflow exists surrounding and flowing past an air vehicle or an airfoil, that are concurrently below, at, and above the speed of sound in the range of Mach 0.8 to 1.0, i.e., 600 to 768 miles per hour at sea level. This condition depends not only on the travel speed of the craft but also on the temperature of the airflow in the vehicle's local environment. It is formally defined as the range of speeds between the critical Mach number, when some parts of the airflow over an air vehicle or airfoil are supersonic, and a higher speed, typically near Mach 1.2, when the vast majority of the airflow is supersonic. Between these speeds, some of the airflow is supersonic, but a significant fraction is not. Most modern jet-powered aircraft are engineered to operate at transonic airspeeds. Transonic airspeeds see a rapid increase of drag from about Mach 0.8, and it is the fuel costs of the drag that typically limits the airspeed. Attempts to reduce wave drag can be seen on all high-speed aircraft, most notable is the use of swept wings. But another common form is a wasp waist fuselage as a side effect of the Whitcomb area rule. Severe instability can occur at transonic speeds. Shock waves move through the air at the speed of sound. When an object such as an aircraft also moves at the speed of sound, these shock waves build up in front of it to form a single, very large shock wave. During transonic flight, the plane must pass through this large shock wave, as well as contend with the instability caused by air moving faster than sound over parts of the wing and slower in other parts. Transonic speeds can also occur at the tips of rotor blades of helicopters and aircraft. However, as this puts severe, unequal stresses on the rotor blade, it is avoided and may lead to dangerous accidents if it occurs. It is one of the limiting factors to the size of rotors, and also to the forward speeds of helicopters' side of the rotor, thus possibly causing localized transonics. Condensation clouds. At transonic speeds, supersonic expansion fans form intense low-pressure, low-temperature areas at various points around an aircraft. If the temperature drops below the dew point, a visible cloud will form. These clouds remain with the aircraft as it travels. It is not necessary for the aircraft as a whole to reach supersonic speeds for these clouds to form. Typically, the tail of the aircraft will reach supersonic flight while the bow of the aircraft is still in subsonic flight. A bubble of supersonic expansion fans terminating by a wake shock wave surround the tail. As the aircraft continues to accelerate, the supersonic expansion fans will intensify and the wake shock wave will grow in size until infinity is reached, at which point the bow shock wave forms. This is Mach 1 and the Prandtl-Glauert singularity. Transonic flows in astronomy and astrophysics. In astrophysics, wherever there is evidence of shocks, the flow close by must be transonic, as only supersonic flows form shocks. Interestingly, all black hole accretions are transonic. Many such flows also have shocks very close to the black holes. The outflows or jets from young stellar objects or disks around black holes can also be transonic since they start subsonically and at a far distance. They are invariably supersonic. Supernovae explosions are accompanied by supersonic flows and shock waves. Bow shocks formed in solar winds are a direct result of transonic winds from a star. It has been long thought that a bow shock was present around the heliosphere of our solar system. This was recently found not to be the case according to IBEX data.